So now that we have seen the visualization of the definition, let us give finally the very rigorous definition of the limit or the convergence. So we have the sequence an, and we say that this sequence an converges to the real number L, or converges to L is the limit of the sequence, if for every epsilon, right? Epsilon is this accuracy threshold. We can find this natural number n of epsilon that depends, this natural number is dependent upon epsilon, such that, well, remember that we say that the distance between the elements of the sequence and the limit can be made as small as we please, provided that we go far enough. And how far we need to go to attain this threshold depends on epsilon. So for every positive epsilon, there exists a natural number n of epsilon, such that for every natural number n that is greater than this n of epsilon, provided this means that we've went far enough, the distance between the sequence and its limit will be smaller than epsilon, and we denote this by writing this familiar expression that says that the limit of an is L, or that the sequence an converges to the limit L. Now, the only thing that we really needed here to define convergence to a limit is this notion of distance. If we were to replace this absolute value of the difference by any distance function, then we could define the notion of convergence in any metric space. Now, here specifically, we need to think of this again as when we will be proving by definition that a certain number is the limit of the sequence. So a simpler way of seeing this is, because sometimes I know that this absolute value makes things more complicated for the students, is that this means that for every epsilon, two constraints are satisfied, right? This is equivalent to saying that an minus L is smaller than epsilon and bigger than minus epsilon, as we have seen with the visualization with the vertical lines. And this means basically that this system of inequalities is satisfied by infinitely many natural numbers n, and in fact, if it's satisfied, if this system of constraints is satisfied by some number n0, then it is also satisfied by any n that is greater than n0. This is the essence. Okay, so now, for example, let us prove by definition that the limit of the sequence is 0. And so I need to show that the distance of 1 over n and between 1 over n and 0 can be made as small as we please, and provided we go far enough. So to prove this, I need to show that whenever I'm given an epsilon, I have a way of computing how far I need to go, right? Or computing this n of epsilon from epsilon. And this would be, in essence, the proof by definition. So again, what I want to show that the distance, the absolute value of 1 over n minus 0, so here we're talking about positive numbers, so this is in essence 1 over n minus 0 absolute value. So what I want to show is that this inequality can be satisfied starting from some point for every n that is big enough. Okay, so let us think of this as trying to solve this inequality and see that it is satisfiable for all natural numbers starting from some place. Okay, so now we can manipulate this inequality so these are positive numbers. So we see that right away that this inequality is equivalent to n being greater than 1 over epsilon. But of course, n is a natural number. So what we can do here is we can take the floor function, right? We can round it to the nearest natural number that to this value. But then again, we could be decreasing this, but we decrease it by at most 1. So the idea would be that we will define n of epsilon. We'll choose this to make sure that n of epsilon is integer. We will take the integer value, but in order we could have made this smaller, right? But taking the integer value cannot decrease this number by more than 1, so we add 1 to be on the safe side. And now we know that for every natural number n that is bigger than n of epsilon, we will have in particular that this n is bigger than 1 over epsilon. And if n is bigger than 1 over epsilon, this is equivalent to saying that 1 over n is smaller than epsilon. That is, we have proved that for every epsilon, there is a way we can compute n of epsilon by this formula, and then every natural number n that will be greater than this n of epsilon, we will have this constraint, we will have that 1 over n minus 0 absolute value is smaller than epsilon, okay? Now let us see this a bit more complicated example for the sequence that we have seen in the visualization. So now I want to prove that the limit of the sequence is 0.6 or 3/5. Okay, and how could I argue intuitively that this should be the limit? Well, supposing that n is huge, like billions, right? So when n is billions or billions, right, then this is negligibly small number with this 2 and minus 1 over n. This makes it like a bit oscillate, but still it's very small number. And what we have here, so if n is a billion, right, then this 2 is kind of negligible. We can ignore this 2. It really doesn't contribute much. Of course, it's not a rigorous argument. I'm just giving you the intuition here. We'll see a rigorous way of doing this. And the same with this 1 over here. We have 5 billion, so we can like kind of ignore this 1. And so what we see here, so it's 3n over 5n. This n is kind of reduces, so it's 3/5 plus something small, which can be made as small as we please. And so it is reasonable, therefore, to assume that 3/5 is this limit, or at least to guess that this is this limit, and now we'll prove it rigorously. So let us remember what I need to prove. I need to prove that this expression can be made arbitrarily small, right? And I can make it smaller than any epsilon that I wish. And this inequality is actually solvable, okay? So we can demand that this is smaller than epsilon, and this inequality starting from some n for every n that is bigger than it is being satisfied. So let's see how it's done. So bringing this to a common denominator, what we have here is that we've basically made a common denominator of this and this, and this remained. Now we can use the triangle inequality, and using the triangle inequality, it's smaller than this plus that. Okay, and now we can remember, or let us just emphasize this point, that what I need to show that such n of epsilon exists, I didn't say that I have to provide you the smallest possible n of epsilon for which it is satisfied. I just need to provide some of those. And so well, now I will make some simplifications that will make it easier for me. And I'll say, well, this expression, if I remove this one, we have this, of course, something positive here. So when we make the denominator smaller, we make the whole fraction be bigger, right? And so I would say that removing this one, this is smaller than this expression, right? And then I can add those two. It's basically 2 plus 7 over 25, and all of it times 1 over n. So if I were to show you that I can make this expression smaller than epsilon, right, for every n that is big enough, then of course I can make this expression as small as I wish. So this means that for every n we have, that this is, after I add those together, so let's follow here, this is smaller than 57 over 25 over n, okay? And now if I, let us look at this inequality. I basically will solve this inequality, and I'll choose n such that this expression is smaller than epsilon. And then if I show it for this sequence, then it follows for this sequence as well, okay? So this is an inequality is equivalent to n being bigger than 57 over 25 epsilon. And again, we want it to be an integer number. So what we can do, we can take the integer value of this and add 1. So we have seen this trick previously. So now for every n that is bigger than n of epsilon, this means that this n is in particular bigger than 57 over 25 epsilon, which means that if we get back that n is bigger than this, and if n is bigger than this, this is equivalent to this being smaller than epsilon. But this expression is bigger or equal to this expression, which eventually means that this distance will be smaller than epsilon. So here's a way of computing this n of epsilon. If I want this to be smaller than epsilon, then let us compute this number, right? Computing this number in the following way, we see this n is dependent on epsilon, and we see that every n that is bigger than of epsilon, this inequality will be satisfied. And this means that we have proved by definition that the limit of this expression is 3/5, because if we wish, right, we wish this expression to be smaller than epsilon, then actually I have shown you a way. If you want this to be smaller than any epsilon, you can achieve this, provided that you make this computation. And this is how far you need to go. Basically, with proving a limit by definition, it's a game. You say, if I want to prove to you that this sequence converges to a particular limit, it's a game that we can play. You say, okay, you claim that this is the limit, then can you prove to me, or can you show me that starting from some place, the distance between the elements of the sequence and the limit is smaller than 1,000? And I say, sure, make this computation, and here's this natural number. And beyond this natural number, all the elements in the sequence, their distance from the limit will be smaller than 1,000. And then you can say, okay, what about 1 millionth? And I say, sure. For 1 millionth, go here, make this computation, and beyond every number n that is bigger than this number, the distance between the sequence and the limit will be smaller than 1 millionth, and it can be done for every epsilon. So let us now go back to our visualization and see how it works with this n of epsilon.